And it doesn't seem to want to get my screen share here up and running. Here we go. The heart pumps approximately 7,000 liters of blood through the body each day, and the heart contracts some 2.5 billion times in an average lifetime. The heart and all the blood vessels make up the cardiovascular system. The blood vessels make up two circuits, the pulmonary circuit and the systemic circuit. In the systemic circuit, that delivers all the oxygen to all body cells and carries away waste. So blood enters the capillaries, and there's a gas exchange in the capillaries. Blood from the lungs is oxygenated, so that oxygen is sent to the tissues, and then carbon dioxide is the waste product and is given back into the blood. So the deoxygenated blood returns to the heart via the vena cava. It enters the right atrium and is pumped out through the right ventricle into the pulmonary arch and through the pulmonary arteries into the lungs. The carbon dioxide is blown off when we breathe, and then the gas exchange in the alveoli in the lungs oxygenates the blood again, and that returns to the heart via the pulmonary veins. It goes into the left atrium, the collecting chamber, and is pumped out through the left ventricle, up through the aortic arch, into the aorta, and distributed to all the body tissues. And then again, the oxygen is used up, and CO2 is given off as waste, and it's carried away into the bloodstream, and the process starts all over again. As far as the structure of the heart goes, it's there are four chambers. The heart's sort of a cone-shaped muscular pump. There's two atria for blood storage and two ventricles, one low pressure, the right side, and one high pressure pump, the left side. This slide shows a view of the size and location of the heart. And here's another slide showing the heart from frontal view. The base of the heart is actually the top of the heart. The apex is the bottom. There are coverings of the heart, including the fibrous pericardium, the visceral pericardium, and the parietal pericardium. The fibrous pericardium also lines the pericardial cavity. And the heart wall itself has three distinct layers. There's an epicardium outer layer, a myocardium middle layer, and an endocardium inner layer. The myocardium is the muscle itself. And table 15.1 shows a chart of the wall of the heart, and showing the epicardium is also considered a visceral pericardium because it actually adheres to the pericardial membrane. The heart is divided into four chambers. The function of the right atrium, it receives blood from both the inferior and superior vena cava and the coronary sinus. The right ventricle receives blood from the right atrium and then pumps from there. The left atrium receives blood from the pulmonary veins. Those are the only veins that carry oxygenated blood in the body. And the left ventricle receives blood from the left atrium and pumps it. Here's a chart of some of the valves of the heart. The tricuspid valve, so named because it has three flaps. And this location is in the right atrioventricular orifice. What it does is it prevents blood from moving from the right ventricle back into the right atrium during ventricular contraction. The pulmonary valve is located at the entrance to the pulmonary trunk and prevents blood from moving from the pulmonary trunk back to the right ventricle during ventricular relaxation. The mitral valve is in the left atrioventricular orifice. It has two flaps. It prevents blood from moving from the left ventricle back to the left atrium during ventricular contraction. And then there's the aortic valve, which is located at the entrance to the aorta. Prevents blood from moving from the aorta back into the left ventricle during ventricular relaxation. This slide shows different views of the different parts of the heart. Interesting to note, chordae tendineae. And the papillary muscles. These extend from the actual endothelial tissue in the endocardium. And here's a couple more pictures. Here's a cross section showing some close-up views of papillary muscles, chordae tendineae, some of the cusp of the valves. And here you see some of the valves. You can see these valves here, ventricular valves and atrial valves. There's a picture of the skeleton of the heart. These are fibrous rings that, together with other masses of dense connective tissue and a portion of the septum between the ventricles, constitute the skeleton of the heart. And this is the path of the blood through the heart. And we're looking at the bottom, we have tissue cells and the systemic capillaries and the oxygen and carbon dioxide exchange. So the deoxygenated blood heads up the inferior vena cava, and then enters the right atrium, and it heads through the pulmonary valve. I'm sorry, not the pulmonary valve there, the tricuspid valve, and then enters the right ventricle, and then heads through the pulmonary valve to the pulmonary arch, to the lungs, through the pulmonary artery, and then there's a gas exchange in the alveolar capillaries. Oxygen is brought in, and when you breathe, and then you breathe off CO2, and there's a gas exchange. So the pulmonary veins bring that blood back to the heart, and the blood heads through the mitral valve, the left ventricle, and then through the aortic valve, up through the aortic arch, and is again distributed to the tissues. The aorta has branches, and those branches distribute blood to either the upper portion of the body or the lower portion of the body. And then it starts all over again. And it's from the top, the deoxygenated blood heads from the superior vena cava back into the right atrium. So there it is, top to bottom. This is a good chart to remember. The left and right coronary arteries supply blood to the tissues of the heart. The right coronary artery supplies the posterior and ventricular artery and the marginal artery, and also the myocardial capillaries in the ventricular walls and the walls of the right atrium and right ventricle. The left coronary artery supplies the circumflex artery and the anterior and interventricular artery, and the capillaries in the left atrium and left ventricle and in the ventricular walls. And then that blood heads to the cardiac veins and cardiac coronary sinus and into the right atrium. And here's some different diagrams, pictures of showing the aortic valve cusps, the three cusps, the right coronary artery that supplies it, the opening of the left coronary artery. That blood would come in from the aorta. I'm sorry, it pumped out to the aorta. And there's some of the heart actions. The heart chambers function in coordinated fashion. When atria contract, it's called atrial systole. Simultaneously, ventricles relax, which is called ventricular diastole. So you have atrial contraction when the ventricles relax. When the ventricles contract, the atria, both of them relax. So you have opposite mechanisms working in tandem. And it shows when you have ventricular diastole, relaxation, you'll have atrial systole, and valves, the tricuspid and mitral valves will open, allowing blood flow, but the pulmonary and the aortic valves will close. Okay, that allows blood to come into the heart, but it's not going to pump out into either the pulmonary arch or the aortic arch. And then when you have ventricular systole, those valves must open to allow blood to flow to either the lungs or the aorta, where it can be distributed in the body. While that's pumping, the atria relax, and the tricuspid and mitral valves must close to prevent backflow into the atria. So during a cardiac cycle, the pressure in the heart chamber rises and falls. In atrial systole and ventricular diastole, blood flows passively into the ventricles. The remaining 30% of the blood is pushed into the ventricles. The AV valves open and the semilunar valves close. The ventricles relax. This causes an increase in ventricular pressure. In ventricular systole and atrial diastole, the AV valves close. The chordae tenonate prevent the cuspid valves from bulging too far into the atria. The atria relax. Blood flows in the atria. The ventricular pressure increases and opens the semilunar valves, and the blood flows into the pulmonary trunk and aorta. I'm sorry. And there's an animation that you can watch that I don't think I can do here. Maybe I can.
Ventricular contraction causes the atrioventricular valves to close, which signals the beginning of ventricular systole. The semilunar valves were closed during the previous diastole and remain closed during this period. Continued ventricular contraction increases pressure in the ventricles above the pressure in the aorta and pulmonary trunk, causing the semilunar valves to open. When the ventricles relax and their pressures drop, blood flowing back toward the relaxed ventricles causes the semilunar valves to close, which is the beginning of ventricular diastole. Note that the atrioventricular valves remain closed. When the pressure in the ventricles becomes lower than the pressure in the atria, the atrioventricular valves open and blood flows into the relaxed ventricles. This accounts for most of the ventricular filling. The atria then contract and complete the ventricular filling. Ventricular contraction causes the atrioventricular.
Okay, so that wasn't, that was pretty interesting. A heartbeat through a stethoscope sounds like lub-dup. The lub is the first heart sound. It occurs during ventricular systole. That is the AV valves are closing. The dup, the second heart sound, occurs during ventricular diastole, and that's the pulmonary and aortic semilunar valves closing. A murmur is just the abnormal heart sound from cusps not completely closing. And this slide just shows aortic area, pulmonary area, tricuspid area, and mitral area. The cardiac muscle fibers form a functional syncytium. This is a mass of cells that function as a unit. Two such areas exist in the heart. In the atrial walls, it's called the atrial syncytium. In the ventricular walls, it's called the ventricular syncytium. Let's look at an animation on action potentials in the sinoatrial node, or the SA node. And it's showing calcium, potassium, and sodium. And, oh, here we go. As okay, it stopped. Oh, there it goes. There's a little spike. Membrane potential going up. And continuing to spike as calcium enters. And that's the relative refractory period. Then it has to drop. As calcium closes, sodium enters, and then we drop below the threshold. And then it goes back to, oh, okay. And it starts over when it hits the action potential. How can I get past this slide? There we go. So here's the cardiac conduction system charted. The SA node institutes an impulse that reaches the atrial syncytium, and it spreads the junctional fibers. At the AV node, there's a bundle of fibers. Those spread out to the bundle branches and Purkinje fibers, and then it heads to the ventricular syncytium. Let's see a good picture of. Let's play this one.
Potentials originate in the sinoatrial node and travel across the wall of the atrium from the sinoatrial node to the atrioventricular node. Action potentials pass slowly through the atrioventricular node to give the atria time to contract. They then pass rapidly along the atrioventricular bundle, which extends from the atrioventricular node through the fibrous skeleton into the interventricular septum. The atrioventricular bundle divides into right and left bundle branches, and action potentials descend rapidly to the apex of each ventricle along the bundle branches. Action potentials are carried by the Purkinje fibers from the bundle branches to the ventricular walls. The rapid conduction from the atrioventricular bundle to the ends of the Purkinje fibers allows the ventricular muscle cells to contract in unison, providing a strong contraction.
Okay, and here's a couple of slides showing the path of the conduction impulse from the SA node to the AV node to the junctional fibers, to gathers in the AV bundle, and then it's rapidly sent through this septum, to either to the right or left bundle branches, and then activates the Purkinje fibers. and heads up to the ventricles. Electrocardiogram, ECG, is recording of electrical changes that occur in the myocardium during the cardiac cycle. It's used to assess the heart's ability to conduct impulses. The deflections in normal ECG or waves include the P wave, which is atrial depolarization, the QRS complex, which is ventricular depolarization, and a T wave, that is ventricular repolarization. Again, the electrical activity counteracts when the atrial depolarization occurs. There's a period of ventricular relaxation, and when ventricular depolarization occurs, there's a period of atrial relaxation. I should go over this with this play.
Increased blood pressure stretches the carotid arteries and aorta, causing the baroreceptors to increase their basal rate of action potential generation. Action potentials are conducted by the glossopharyngeal and vagus nerves to the cardioregulatory and vasomotor centers in the medulla oblongata. As a result of increased stimulation from the baroreceptors, the cardioregulatory center increases parasympathetic stimulation to the heart, which decreases the heart rate. Also, as a result of the increased stimulation from the baroreceptors, the cardiovascular center decreases sympathetic stimulation to the heart, which decreases heart rate and stroke volume. The vasomotor center decreases sympathetic stimulation to blood vessels, causing vasodilation. The vasodilation, along with the decreased heart rate and decreased stroke volume, bring the elevated blood pressure back toward normal. If the initial problem were a decrease in blood pressure, the activities and effects of the baroreceptors, cardiovascular center, and vasomotor center would be the opposite of what is illustrated.
Okay, so here's a EKG or ECG, and we start with the action potential. And then we see the atrial depolarization. Then we see the ventricular QRS depolarization down at E. And then when we have a full depolarization, it ends at the S, and then it starts to flatten out. And when the ventricles are fully relaxed, we get the T wave, and then we'll start with a new P with the atrial depolarization in slide C. It's fully depolarized in slide C. This chart shows a little bit of the different, we see the pressure changes, we see the heart sounds, we see the volume, we see the pressure rising from the start of the ventricular systole, all the way from almost 0 to nearly 120 milligrams of mercury, and then it relaxes again as we enter ventricular diastole, and then we have the period of atrial systole that comes up shortly after, and then we start the whole cycle over. You'll notice the atrial systoles are shorter periods than the ventricular systole because it takes longer to complete the QRS than it does the P. And there you see the lub, dup sounds. AV valves close during systole, and the semilunar valves close during diastole. Okay, the SA node controls the heart rate. There's also sympathetic and parasympathetic fibers that control the heart rate as well. There's also regulatory reflex centers that influence heart rate. And there's some additional factors that may influence heart rate that include physical exercise, your body temperature, concentration of various ions, including potassium and calcium. Parasympathetic impulses decrease heart action, while sympathetic impulses increase the heart action. And the cardiac center regulates the autonomic impulses to the heart. So it keeps the regularity of pressure and heart rate. And as we heard in the slide, you have a receptor that sends a message to via sensory or afferent neuron to your CNS, and that's going to send a message to the motor or efferent neuron, to the effector muscle or gland. And it talked about the parasympathetic vagus nerves influencing heart action. There's an action potential animation here. It's going to be pretty similar to what we just saw before, sodium, calcium, and potassium. So sodium channels open, we got a spike. Calcium channels open, we get a spike below the threshold. And then when the potassium is opened and goes out of the membrane, it spikes forward and goes up. And that's it. And let me have trouble with this. Okay. Okay. Our next slides are going to deal with arrhythmias. Oh, that was not there. It's clinical application about arrhythmias. Okay, so I don't have a slide for that. Let's talk about the blood vessels. The anatomy of the blood vessels. There are blood vessels. They're organs of the cardiovascular system. The blood vessels form a closed circuit to and from the heart. Blood vessels include the arteries, which carry blood away from the ventricles of the heart towards the body. There are arterioles that receive blood from the arteries and carry blood to the capillaries. And capillaries are the site of exchange of substances between the blood and the body cells. The venules then receive blood from the capillaries, and the veins carry the blood toward the atria of the heart. These are pictures of the differences between veins and artery. As you notice, the smooth muscle in the artery is much wider than the smooth muscle in a vein. Veins also have valves, some veins. The tunica externa, tunica media, and the tunica interna are pretty much the same. The veins have larger lumens. And we'll talk about a little bit of the arteries. Have 3 layers or tunics. They have an endothelial lining. There's a middle layer of smooth muscle and elastic tissue. There's an outer layer of connective tissue. They carry blood under relatively high pressure. Well, the arterioles have thinner walls than an artery. They also have endothelial lining. The middle and outer layers are thinned. There is some smooth muscle tissue. They have a small amount of connective tissue, and they help control blood flow into a capillary. And here's a little bit of our arterioles with the smooth muscle cell ring. The capillaries are the smallest diameter blood vessels. They connect the smallest arteriole and the smallest venule. They are extensions of the inner lining of the arterioles. The walls are endothelium only, and they are semi-permeable to allow for gas exchange. And here's a little bit about the capillaries. There's a slide of a capillary showing the cell cytoplasm of the lumen of the capillary. And here's another picture of arteriole joining with the venule, and you can see the capillary web that connects the two. This talks about the outward force, including hydrostatic pressure, and inward force of osmotic pressure. They have a net outward pressure of 11 milligrams of mercury, and that's in the arteriole. And then the net force at the venule end, there's an outward force of 16 millimeters. Well, you have an inward force of 24. So the inward force is stronger, and the net pressure inward is 8. And that this is allowing for the gas exchange. It just talks about a little bit of venules and veins, just a little bit of anatomy. Venules are microscopic vessels that continue from the capillaries and merge to form veins. Thinner walls and arterioles, they have less smooth muscle and less tissue than arterioles. The veins are thinner walls and arteries. They still have 3 layers of tunics. The middle wall is poorly developed. Many have flap-like valves. They carry blood under relatively low pressure, and they function as blood reservoirs. And here's it shown toward the heart. Either from the top to the bottom, and showing the percent distribution. 70% of the blood is in the large and small veins and venules. 12% of venous blood is in the lungs. The heart gets 8 to 11%. Systemic arteries 10 to 12%. Capillaries 4 to 5%. And then here's a chart of different characteristics of the blood vessel. Blood pressure is just the force that blood exerts against the inner walls of blood vessels. Arterial blood pressure rises when the ventricles contract and falls when the ventricles relax. Systolic pressure is the maximum pressure during ventricular contraction. When your heart beats, that's the top number, is pressure in your arteries when the heart is beating against the arterial walls. When the heart relaxes, the bottom number is the diastolic pressure, which is the minimum pressure when you're not pumping blood, when the ventricles relax and the blood's not being pumped. And just a slide of different arteries of the body: temporal, carotid, brachial, radial, femoral, popliteal, posterior tibial, and dorsalis pedis. And there's a clinical application on blood vessel disorders in your text. So here's the factors that influence arterial blood pressure. Blood volume increases, blood pressure increases. Heart rate increases, blood pressure increases. When stroke volume increases, blood pressure increases. When blood viscosity or thickness increases, that also increases blood pressure. When your peripheral resistance increases, that increases blood pressure. And there's also a clinical application on the measurement of arterial blood pressure in your text. Another one on space medicine. Okay. The blood pressure is determined by cardiac output, CO, and peripheral resistance. According to this relationship, blood pressure BP equals CO times PR. So the maintenance of blood pressure requires regulation of these two factors. So when blood pressure increases, the heart responds by decreasing its rate and decreasing stroke volume. That decreases cardiac output. There's increased peripheral resistance, and blood pressure is maintained. When blood pressure is decreased too far, the heart increases rate, increases stroke volume, which increases cardiac output, and peripheral resistance is increased, and blood pressure is maintained. So either you can start out with high blood pressure or low blood pressure, and the body responds. So cardiac output increases, blood pressure rises, the baroreceptors in the aortic arch and the carotid sinuses are stimulated, sensory impulses are sent to the cardiac center, parasympathetic impulses are sent to the heart, the SA node is inhibited, the heart rate decreases because of that, and blood pressure returns toward normal. If there's rising blood pressure, the stimulation of baroreceptors in the aortic arch and carotid sinuses, sensory impulses are sent to the vasomotor center. The vasomotor center is inhibited. There's less frequent sympathetic impulses to the arterial walls. There's vasodilation of arterioles. There's decreased peripheral resistance, and blood pressure returns toward normal. And here's an animation of that. Just going to do that. Blood's pumping. Flow stopped. So let's talk about venous blood flow. The blood pressure decreases as the blood moves through the arterial system and into the capillary network. So little pressure remains at the venular ends of the capillaries. This is only partly a direct result of heart action. It's dependent on skeletal muscle contraction, your breathing, and venoconstriction. All veins except those returning to the heart from lungs drain into the right atrium. This is the pressure in the right atrium. The factors that influence it alter flow of blood into the right atrium. That affects pressure within the peripheral veins. A weakly beating heart will increase central venous pressure. Increase in central venous pressure causes blood to back up into peripheral veins. This can lead to peripheral edema. And there's a clinical application 15.6 on exercise in the cardiovascular system. Let's talk about the passive circulation. The blood vessels can be divided into two major pathways, the pulmonary circuit and the systemic circuit, which includes the coronary circulation. And here's a look at the pulmonary circuit of the lungs. Again, we talked about this earlier a little bit. Blood coming from the superior and inferior vena cavas going into the right atrium, being pumped through the right ventricle, through the pulmonary arch, via the pulmonary artery into either the left or right lung. And then there's gas exchange that takes place. And then the left or right pulmonary veins, send it back to the left atrium, back to the left ventricle, up through the pulmonary semilunar valve, and we get to the aorta. The aortic semilunar valve, and we get to the aortic arch and to the aorta, and the aortic branches spread oxygenated blood to various parts of the body. And here's another one, a little bit different view, the blood flow. It's showing blood going to the alveolar capillary. There's a slight net outflow of fluid from the capillary. Solutes fail to enter the alveoli but contribute to the osmotic pressure of the interstitial fluid. Any excess water in the alveolus is drawn out by the higher osmotic pressure of the interstitial fluid. Fluid from the interstitial space enters the lymphatic capillary or the alveolar blood capillary, and it heads either to the lymph or to the blood system. Systemic circuit is composed of vessels that lead from the heart to all body parts except the lungs and back to the heart. It includes the aorta and its branches. It includes a system of veins that return blood to the right atrium. And here's a look at the arterial system again. There's some more arteries besides the ones we saw earlier. Some of the ones you might see more commonly mentioned are the common iliac, the external iliac, and the internal iliac. There's also the external, internal, and common carotids and the vertebral artery. Oh, the brachiocephalic too. And here are the principal branches of the aorta. You have the ascending aorta, the branch, right and left coronary arteries. And then you have the arch. You have breaks into the brachiocephalic, the left common carotid and left subclavian. And then the ascending aorta. It's the thoracic aorta. And there's the different arteries there. And then the abdominal aorta and its different branches. And here's another picture of the veins coming down from the head and the aortic arch. You can see the left common carotid, the left subclavian, and then you have the brachiocephalic, which branches to the right common carotid and the right subclavian. And then that's the descending portion of the arch down here. And here's some of the, this is some of the gastrointestinal arterial network. You can see the splenic artery. And then here's the hepatic artery. And you can see the common iliac, and it's going to branch left and right into the femoral arteries. And then just some different pictures of the arteries of the brain, head, and neck. And there's the blood supply up to the head, the arteries. And here's some arteries to the shoulder and upper limb. Let's start with the right subclavian, and then from there it branches down the axillary, and again we have a brachial and radial branch coming down, and then we have a radial and ulnar branch coming down. And here's some of the arteries to the chest and abdominal walls. You know, a little bit showing wrapping around the vertebral bodies, and then the sternum. And some arteries to the pelvis and lower limb, front and back view. And then there's the venous system, which kind of overlaps a little bit of the arterial system. The characteristics of the venous pathways, the vessels of the venous system originate with the merging of capillaries and venules into small veins, and small veins into larger ones. Unlike arterial pathways, those of the venous system are difficult to follow due to irregular networks and unnamed tributaries. And here's the veins from the brain, the head, and the neck, and the veins of the upper limb and shoulder, and the veins from the abdominal and thoracic walls, and the veins from the abdominal viscera. And here's again showing how how everything is connected via capillaries. The mesenteric artery, for example, goes to the intestine, and then the splenic artery also goes in the same pathway, parallel. There's gas exchange, and that blood heads to the hepatic portal vein, and through the liver to the hepatic vein, to the inferior vena cava, and eventually back to the heart. It's a good slide, though. It shows the path of deoxygenated blood and oxygenated blood. And some veins of the lower limb and pelvis. Okay, some of the changes that occur in arteries and veins during your lifespan. There's cholesterol deposits in the blood vessels, heart enlargement, especially the myocardium, death of cardiac muscle cells. Happens occasionally through ischemia, even myocardial infarctions. Increase of fibrous connective tissue of the heart, increase in adipose tissue of the heart, increase in blood pressure, and decrease in the resting heart rate. Some of the lifespan changes that can happen. And 15.7 is a clinical application of molecular causes of cardiovascular disease. And then there's a clinical application of coronary artery disease. So, some of the outcomes that have to be assessed for this chapter. You should know the functions of the organs of the cardiovascular system: the heart, the arteries, the veins, the arterioles, the venules, and the capillaries. You should be able to identify the various coverings of the heart and the layers that compose the wall of the heart. Be able to identify and locate major parts of the heart and discuss the function of each part. What do the ventricles do? What do the atria do? What do the valves do? You should be able to trace the pathway of the blood through the heart and the vessels of the coronary circulation. You should also be able to describe the cardiac cycle and the lub-dup sounds. How are those sounds produced? Identify the parts of a normal ECG pattern and discuss the significance of the pattern. The PQRST, explain how the cardiac cycle is controlled. Blood vessels, you compare the structures and functions of the major types of blood vessels and describe how substances are exchanged between blood in the capillaries and the tissue fluid surrounding body cells. Explain how blood pressure is produced and controlled, and describe the mechanisms that aid in returning venous blood to the heart. You should be able to compare the pulmonary and systemic circuits of the cardiovascular system. You should be able to identify and locate the major arteries and veins, and be able to describe some of the lifespan changes that happen in the cardiovascular system. And in-class assignment for this week is read chapter 16. And that ends our discussion on the cardiovascular system. Next week, I will be going over chapter 16. And I look forward to seeing you then. It'll be same time next Monday.